there is a relationship between an inverse and the derivative of an inverse that will allow us to calculate derivatives even if we don't know what the inverse is. And so we'll see an example of that where we have a function that is pretty nasty to try to find the inverse of, but we'll be able to find specific derivative values for its inverse because of this relationship. So without further ado, let's jump right in. Advanced. I do need to turn this guy on.
Do you have a lot more school that show up on Tuesday or Wednesday?
More than two, yeah. You get 6. Sean,
This late in the year?
Sean, Katie, Nathan, Sandrine, James. Somebody, missing somebody maybe. 5 or 6. Okay. That's it, James. This is 5.1 concluded. Hopefully we'll conclude it. We should conclude it. 5.1 concluded. Oh, look at that. And then there were 3. Okay, so as I said, there is a relationship between inverses and their derivatives. So that's what we're going to start is with 5.1.7 theorem, which states that relationship. And it has us supposing, always a dangerous thing to do, suppose that the function that we'll call f is continuous and monotonic. It's a fun word, monotonic. On some interval from a to b. Oh, Mr. Lopez. His pen is not doing its job properly. And we're going to specify that y is our dependent variable here. Y depends on f of x. If the derivative of f exists and is non-zero, on that interval, then the derivative of the inverse this is where the whole solving for x thing yesterday sort of comes into fruition. The derivative of the inverse, where we're going to let the inverse of f is x equals f inverse of y. Its derivative is given by dx dy is equal to 1 over dy dx. Ugh. be righteously careful here. Righteous. Okay. Dx dy. What's dx dy? Okay, dx dy is the derivative of x, this inverse function, with respect to y. Let's be crystal clear on that. So this is going to make us kind of uncomfortable, but we're going to call this f inverse prime of y. So the derivative of the inverse with respect to y, dx dy. dy dx is f prime of x. Because again, y is equal to f of x. Okay, so it establishes this reciprocal relationship, which we'll see with specific numbers in just a second. We're going to start from this pretty general place, because this general statement of this relationship allows us to then find those specific situations. And we're like, okay, but why are the x's and the y's? Let's do an example and see what this looks like. And the example is tricky and you're not going to like it, but I think it will illustrate what's going on. And kind of put, do we want to put this? We're going to leave it at that. We're going to see this in action with example 5. It's going to be a doozy. Example 5. Suppose we have f of x equal to 2x plus 3 divided by x minus 1. Did we do the example? Did we find the derivative or the, yeah, so we did find the inverse in example 4. So we'll come back to that. The derivative of f, quotient rule, is going to be, this is the derivative of f twice the derivative of the numerator times the denominator minus the derivative of the denominator, which is just 1, times the denominator, all divided by the denominator squared. Well, distributing this, we get 2x minus 2. The 2x's cancel out. Negative 2 minus 3 is negative 5. And so the derivative of this guy is negative 5 over x minus 1 squared. Allegedly, if we put this guy underneath 1, that's going to be the derivative of our inverse. Well, we're not going to reinvent the wheel. We solve for f inverse of x in example 4 yesterday. Believe me, you can go back to example 4. We use this method where instead of swapping our variables like we did in algebra 2, we actually just solve for x, because the inverse needs to undo all the stuff that has been done to x to give us y, so that we can then get x given the y, because we have this undoing relationship in our inverse. Crucially though, for this proof or for this example to work, we are not going to use the swapped version where we sub back in the variables that we wanted. We're going to use this guy. We're going to use this guy. We're going to say that our inverse is x equals y plus 3 over y minus 2. And found x is equal to y plus 3 over y minus 2. So if I gave you some random x value and did all this stuff to it, the value that pops out, if you then do all this stuff to it, add 3 and then divide by that value divided by 2, it'll give you back x. Undoes those operations. This is what we're going to calculate the derivative of, because our formula, our theorem says we want the derivative of x, this guy, with respect to y. Well, that's something we can do. We can calculate the derivative of this right side. Specifically, we want dy of y plus 3 over y minus 2, which again requires the quotient rule. We want the derivative of the numerator, y plus 3, with respect to y, which is 1, times the denominator, y minus 2, minus the derivative of the denominator with respect to y, again, just 1, times the numerator, y plus 3, divided by the denominator squared. Quotient rule. So let's simplify this. We get y minus 2 minus y minus 3. The y's are going to cancel here. We're going to get a negative 2 minus 3, which is negative 5 over y minus 2 squared. Where are we at? We've got this expression up here, f prime of x, and we've got this guy down here, which is the derivative of x with respect to y. We're being told in theorem 5.1.7 that this guy is the reciprocal of this guy. Well, that's problematic because we're not dealing with the same variables. Ew. How do we verify that this theorem is actually correct? I'm not seeing it. I'm not seeing that if you throw this guy underneath a 1, that you'll spit out this guy. Well, that starts with this problem of having y in here instead of x, because we can't do an apples to apples comparison. And so that's what we're going to do. We're going to make an apples to apples comparison by transforming this into an expression that involves x. Well, we're just going to randomly plug in x's here. No, we know what y is. Y, in the context of this problem, is this guy, this original function. So we're going to plug that in for y and see what happens. Or not just see what happens, but hope that what happens is we end up with the reciprocal of f prime of x. So let's get to that somewhat onerous task. So negative 5 over y, we're going to plug in the function f for y, 2x plus 3 over x minus 1 minus 2 squared. Yuck. I think our game plan here, and let me just mark this is happening because y is equal to 2x plus 3 over x minus 1. I'm thinking we should probably make this into a single fraction before we square it. So I'm going to multiply this 2 by x minus 1 over x minus 1 to get that we have negative 5 over 2x plus 3 minus 2 times x minus 1 all over x minus 1. That is what we're going to square. Because remember, if we do a quick check, dividing this into both things, we end up with 2x plus 3 over x minus 1. Dividing this part, the x minus 1's cancel, we get negative 2. Okay. So now this turns into, we're going to square top and bottom. And then because we don't really like these triple fraction deals, I'm going to flip this denominator into this numerator. So this is going to become negative 5 times x minus 1 squared. So I squared both of these things, and then flip that up. And then we need to still square 2x plus 3 minus 2x plus 2 squared. Oh, well, this is going to be kind of nice. Stuff cancels. 2 x's, namely. What we get is negative 5 times x minus 1 squared, all divided by, what's left down here? A 3 and a 2. Oh, dang. Check out this black magic. 5, 25. This 5 cancels. And what we're left with is negative x minus 1 squared over 5. What? Now, comparing this to our derivative of f, the apples to apples comparison, that does look quite a bit like the reciprocal of f prime of x. So we have confirmed that this is indeed 1 over dy dx. Is this going to be a huge focus on our chapter 5 test? Probably not. It's a huge focus on your homework. I think you have one problem with this specific situation. So if you're sort of anxious, apprehensive, what's the third A word that means those two things? I don't know. If this was kind of like, I'm not that stoked on it, don't fret too much. Okay? The second part of today's lesson is something that we'll be focusing quite a bit more on. Okay, but basically, inverses are reciprocals. Their derivatives are reciprocals of each other's, which kind of makes sense. Questions, thoughts, feelings?
Can you explain each of the things that we found, what they are? Does that make sense? For the first part, we found the derivative of f.
The first part is the derivative of f.
Okay.
The second part is the derivative of its inverse, but keeping this notation, keeping this idea of the inverse is taking my domain values of, my range values of f and spitting back my domain values.
Okay.
And so we're taking that literally with respect to y. So this is the derivative of the inverse in sort of its very literal taking my y values and changing them back into x values.
Okay.
And that's going to be where we're going with this is if I give you the derivative of a function at a specific value, you can find the derivative of its inverse at the associated range value. And this is the part where our brains are going to kind of go a little haywire if they haven't already, that we're going to have this swapping idea, that this relationship is going to specifically allow us to say, okay, if I know the derivative at a specific point on f, I can find the derivative of an equally specific point on its inverse. But there's a direct relationship between what points those are. And it's domain range, range domain. Let's just keep going and hopefully it'll kind of start to clear. Like I said, this is probably one of my least favorite lessons to teach just because they're kind of intricate. But when we see some numbers, I think it might help us. And so we're going to do 5.1.8 is the theorem that puts some meat on these bones, so to speak. 5.1.8 theorem. Says, suppose the function f is continuous and monotonic on AB. Continuous and monotonic guarantees the existence of a inverse, and this interval contains some c, and suppose or let the function value at c be d. C be d. So f of c is d. This is not written in your theorem, but I want to point this out early in this theorem. If f of c is equal to d, the fact that we have a continuous monotonic function means f inverse of x exists. And specifically, if f of c equals d, then f inverse of d is going to equal what? Remember this relationship we have with inverse functions. You put in a c to f and you get out a d. What happens when you take that value d and put it into the inverse of f? What should it give you? Somebody knows. Somebody knows. C. Or put another way, CD, that point, is on f, and DC is on inverse of f. And so that's a very kind of crucial understanding to have, that if f of c equals d, then we have an inverse point on our inverse function dc. Now, to the actual derivative part. If the derivative of f at c, so the derivative of f at c exists, I mean, it's not some rational function that blows up our numerator or denominator. And if it's non-zero, not equal to 0, then, so the derivative at c on f is some number, then we know that the inverse, and the notation here gets a little tricky, f inverse prime, so the derivative of our inverse at d exists, and specifically that derivative at d is the reciprocal of the derivative of f at c. Lot going on here. So the derivative of the inverse at d is the reciprocal of the derivative of f at c. CD being a point on f, DC being a point on f inverse. I know that's kind of like, what in the what? I think a quick visual intuition on this is helpful before we do a couple examples. So if you have your books handy on page 430, I think we can make work of 430. There's a figure 10. What we have in figure 10 is this function x cubed, and we have its inverse, the cube root of x, also graphed. So the dark line or the dark curve is x cubed, the gray shaded line is cube root of x, which is the inverse of f. And the illustration is mostly meant to show this reflective property of our inverses, that they are reflections of each other over the line y equals x. But I think they can also be instructive in illustrating what this theorem is telling us. That if we have a non-zero derivative at a certain point on f, so for example, the derivative of f at 2 is the slope of our tangent line to the graph at 2, which I suppose we could find that exact value. It would be 3x squared, where we plug in 2 for x. That would be 12. That's a steep line. Okay. What this theorem is telling us is that if we go to this function value, this 8, so just vandalize our books. This is CD. That's CD. There is a tangent line here. There is a tangent line here. There is a tangent line there whose slope is f prime of c. I already regret this. This is not going to dry. Right. So the relationship here is that if we then go to DC, specifically 8,2, this is DC. This theorem says that the tangent line at this point tangent line at this point is going to have a slope that, yes, is f inverse prime of d, because that's where you are, but this is equal to 1 over f prime of c, which without doing the specific values here, that kind of checks out in our brains. That this looks like a pretty steep positive slope, which I think it's like 12. This looks like a pretty gradual positive slope that I would kind of buy it if you told me it was 1/12. Okay, so this reciprocal relationship starts from the reciprocal relationship of our domain and range values of our inverse functions. Okay. Does this make a little more sense? Okay. So the inverse relationship of our derivatives as a graphical translation. So let's see what this looks like in practice. What are we going to do? What are we going to do? Actually, I meant to do, we're going to do illustration. We're not going to do 10. 10's a little weird. We already did 5. Let's do illustration 12. And then possibly, yeah, we'll have time. We'll have time. We've always got time. So illustration. Illustration 12. Or actually, should we just do the problem that we just did? No, illustration 12. Okay, so if we let f of x equal, thank you, zoomed in too much. Let f of x be this big burly polynomial, x to the 5th plus x cubed plus 2x minus 2. Well, first, before we get too far ahead of ourselves, we're going to take a second to do something that we didn't do yesterday, which we were taking the existence of our inverses somewhat for granted, but there is a way to verify analytically without graphing this thing that the inverse exists, because we need a function to be monotonic, always increasing or always decreasing, in order to have an inverse for that function so that it can pass the horizontal line test. Well, we have calculus, which allows us to find derivatives. And this is going to be helpful because we need the derivative in this problem anyway. The derivative of this function is 5x to the 4th plus 3x squared plus 2. Now let's consider for a second. Is there any value for x that when you plug it into the derivative is going to give you a negative number? All of your x values are being either 4th powered or squared. What happens when you take a negative number and take it to the 4th power? It becomes positive, and when you square a negative number, always positive. So we can correctly conclude that this derivative is always greater than 0. What does a derivative that is always positive tell us about how our function behaves? Always, the function is always increasing. Okay. So because f prime of x is greater than 0, for all x, f of x is always increasing monotonic, and therefore we know that the inverse of f exists. Okay? It's not safe just to say, oh, this is a 5th degree polynomial. I know this is a Travolta. Those things have increasing characters, because they don't always. You can certainly have a Travolta that might pull one of those gizmos, in which case we would not be able to invert that function. So you need to actually check the first derivative. Okay. Consider x equals 0. F of 0, plug in 0 for for x, and we get -2. Which means that 0, -2 is a point on f. Also, we should have done this already, but take a moment to consider the futility that would ensue if we tried to compute the inverse of f. Think about that for a second. If we tried to solve for x, literally sit there, look at that function and think, how would you even do that? How would you get x by itself in that polynomial function? Answer is you wouldn't. And so we're going to pull some magic here that without knowing what f inverse is, we can still find some of its derivatives based on what the derivative of f is. So even though we don't know what this inverse function is, we do know that 0, -2 is on f. So as a result, -2, 0 is a point on f inverse, even without knowing what f inverse is. And more specifically to our point, if we wanted the derivative of our inverse at -2, this theorem allows us to find it. If we want the derivative of our inverse at -2, we can apply 5.1.8. I guess maybe I should have done this explicitly. 0, -2, those are C and D. -2, 0, D and C. So f inverse, its derivative at -2 at our D, according to this theorem, is going to be the inverse, the reciprocal of f prime of 0. Why 0? Because 0 is that C. Okay? It's the domain value that got us this range value that became the domain value in f inverse. So all we need to do to find this specific derivative value of the inverse is calculate this derivative value of f, which we can do quite easily by plugging in a 0 here, f prime of 0 is equal to 2, and this is equal to 1/2. So without knowing what this function is, what its formula is, what its equation is, we're able to compute specific derivative values for it by knowing what the derivative of f is.
Would it be -1/2?
Yes, thank you. No.
Yeah,
Because we're looking at the derivative. So f prime of 0 gives you 2. So
did you mean to switch the sign on that then?
so this -2 goes away when we differentiate.
Oh, yeah.
This 2 is coming from, yeah, no, that's confusing. This 2 is coming from the 2x.
Yeah, sorry.
No, that's what it looks, especially since they're right on top of each other.
Yeah.
Okay. So then, finalmente, I think we're just gonna do one more. So this was kind of a contrived example where we started out with a point on f, and then we just conveniently were looking for the derivative of that y value. But what if they just gave us this function and we're like, hey, find the derivative of the inverse at a specific value? How could we do that? Do we have room here? Yeah, we'll have room. Okay, so this is example 6. Same function as our illustration. X to the 5th plus x cubed plus 2x minus 2. But now they're going to be specific. They're going to say find the derivative of the inverse at 4. At 4. Well, that's a fish of a different color. Because now we don't know what c is. We don't know what value gets plugged into f to give us 4. Okay, they've given us, this is the d. We need to figure out when does f equal 4? Specifically, what value c generates a value of 4, because then theorem 5.1.8 opens the door for us to be able to say that this derivative that we are seeking, the derivative of the inverse at 4, would be 1 over the derivative of f at that c value that generated 4. CD, DC. CB, DC. We need the C. We have the ability to at least think about how that could work. If f is this whole guy, plugging in c, we get c to the 5th plus c cubed plus 2c minus 2, and we want this to be 4. Well, that's a hard problem to solve. It's a little bit easier if we set it equal to 0. A little bit easier if we set it equal to 0. Minus 6 is equal to 0. Because now the values of c that will make this function equal to 4 are the values that will make this thing equal to 0. And we have some pretty refined techniques and tools at our disposal that will help us find roots of polynomials. Specifically, our TI-84 graphing utility. So, let's see, y equals x to the 5th, where am I? Plus x to the 3rd, plus 2x minus 6. Let's use window, let's do zoom standard and see what happens. Okay, that actually wasn't bad, but we can make that maybe a little closer. Window, let's do like, I don't know, -5, 5, and -5 to 5. That should be sufficient. Okay, so we want to know what is that? Because that is the C value that when we plug into our function gives us 4, because that is the C value where this guy has a root. All right. So we do have a trace, second trace 0. They want the left bound. And they want the right bound. I'm going to do a little guessy. Sure. So we're being told that the 0 of this equation is at 1.1612414. And we're going to use all of those digits because we want to be thorough. C is equal to 1.1612414. So this is the C value that we will then use over here. So we want F prime of C now. That's kind of nasty because F prime of X is this guy up here. But we do have a graphing utility. So I think the best way to do this, let's skip this part for now and just say that F inverse, the derivative of that at 4, is the reciprocal of the derivative of F at this C value, 1.1612414. So the question is, how do we make that a less onerous task to compute? Here's what I'm going to do. I'm going to, on my graphing calculator, I'm going to take this value 1.1612414. I'm going to store it. Stow it in X. Now if I pull up X, it's got that value in it. And then I'm going to do this calculation using X instead of having to plug this in. Okay, so we get 1 divided by, using the derivative here, 5 times x raised to the 4th power plus 3x squared plus 2. Whew. Now we press enter. That should give us the derivative of our inverse at 4. 0.06606. And we're going to do an approximate here. We did cut off some digits. So that's kind of nifty. We can find arbitrary derivative values for a function that we don't even know what the function is. Thanks, calculus. Letting us do cool stuff. And rather than force this last one, I think we're going to call that well and good. I believe with that, you should be well armed enough to complete the 5.1 assignment, which will be due on Tuesday. Questions, thoughts, feelings? Zoom lines? Nothing. Okay, look at that. Done before the bell today. What are the chances of that? Mario's celebrating. Well, on that note, I hope you all have a wondrous, wonderful weekend. Make good decisions, be safe, and we'll see you bright and early on Tuesday. Thank you.
Thank you.
De nada.